Hello. So we'll begin the fourth lecture in this series. I'll begin by talking a bit about implications of the inverse function theorem, and then briefly discuss C infinity functions with compact support, and then we'll see some constructions involving these. Alright, so let's start. So last time I mentioned the following consequence of. So last time I mentioned this. First one is that if U in Rn is open and F is a C1 map such that the derivative of F, which is a linear map from Rn to Rn, has rank n at all points P for all P in U, then inverse function theorem will imply that the image of U is open in Rn. So today I'll start by mentioning another immediate corollary of the inverse function theorem. So again I have a smooth map if F from U is again an open subset of Rn, like the first one, and if you have a C1 map with such that DFP from Rn to Rn has rank n for all P in U. Now we make an additional assumption that F is injective. In other words, i.e. F is 1-to-1. The conclusion is then F inverse, which is a map from F of U back to U, is also C1. Oh, I see. Also C1. Well, I'll just remark that this when to even say that some map is C1, one needs a domain to be an open subset of Rn. Now the first corollary guarantees that F of U is open in Rn. So it does make sense to say that F inverse is C1. But the point is this assumption that the derivative has rank n for all P is essential for this result to hold, as the following simple example shows. If we drop this assumption, remark, consider F from R to R, F of t equals t cubed. Obviously this is C1, F is C1 and injective, but F inverse of t is which is given by t to the power 1/3 is not differentiable at t equals 0. So even though the inverse may exist, even though the function may be C1 and its inverse may exist, the inverse may not be differentiable. What the previous corollary asserts that if the function is differentiable and the derivative is an invertible linear map, then of course inverse function theorem will tell us that the inverse is also differentiable. So, but one must keep this simple-minded example of f of t is equal to t cubed in mind. Now, I will briefly talk about another major implication of the inverse function theorem. So, to do that, first I have to define the notion of a diffeomorphism. A map from, notice that for this definition I require that the domain is an open subset of Rn and the target is also exactly that same Rn. So a map from here to here is said to be a diffeomorphism onto its image f of u if, well, first of all, f is C1, second f is bijective, as a map from and the third thing is f of u is open and f inverse from f of u to u is also C1. So notice that by the previous observation, an injective f from u to Rn with invertible derivative for all p in u is a diffeomorphism onto its previous observations. Let me make it observations here. Observations, diffeomorphism onto its image, because the previous two observations tell us that the image, under the condition that the derivative is invertible, the first corollary told us that f of u is open, which was one of the requirements for the diffeomorphism, and the second corollary told us that f inverse is also C1. A diffeomorphism is also referred to as a coordinate change. And the reason for that is Well, you have an open set U and F maps it to some other open set f of u. So to begin with, of course, one has coordinates. Let's say this is an open subset of Rn. So I have, for instance, I have Euclidean coordinates for every point in U. But since f is a bijective map from U to f of u, corresponding to every point here, I'll get exactly one point in f of u, and that new point has, well, some other Euclidean coordinates. So essentially what you have done is, if you think of a point as being identified by its coordinates, the coordinates have changed under f. And everything happens in a smooth way. That's the point about saying that f is C1 and f inverse is C1. Now with this in mind, let us state another major corollary of the, so I'll label it as 3, of the inverse function theorem. This is sometimes referred to as the constant rank theorem. Constant rank theorem. So again the setup is U is an open subset Now one major change is I no longer require the target to be Rn again. So let be an open subset and f from U to some other Rm be a C1 map. We demand now that suppose that the derivative dfp, which is a map from linear map from Rn to Rm, has rank k for all p in U. The point is that this rank, this k should not depend on the point p. At every point it is the corresponding linear map should have the same rank for all p in U. Then what the theorem says is that we can change coordinates on U and on the target, so that after composing with this new coordinates, f assumes a very simple form. Then given p naught in U, there is an open set V which contains P naught and is contained in U, and an open set W which contains f of P naught and coordinate changes and diffeomorphisms well, to illustrate what is going on. So let me, so here this is my original U, And so let me not label, let me not draw an open set here. Let me just start with U here and F. So I started with some P naught that goes to F of P naught. Now I am saying that there is a V, smaller open set V, and some W here, and diffeomorphisms phi from this V to V1, C from W to W1. So let me just change the picture slightly. So this is V that is getting mapped to V1 by this phi, and this is C that's getting mapped to W1. So recall that this V1, by the definition of a diffeomorphism, this V1 has to be an open subset of Rn, and this has to be an open subset of Rm. Okay, so this is the picture, and diffeomorphisms like this, such that when I look at the composition is so I have three maps now. One is the original F, then I have a diffeomorphism phi and a diffeomorphism C. Well, I can start by looking at phi inverse. So I'll go from V1 to V, then I compose with F, and then I'll compose with C, such that so first is phi inverse, then F, then C. This is going to let's see, the claim is that this is a very simple map. So x1 xn, so I just started with some point x1 with Cartesian coordinates x1 up to xn inside V1. This has the form x1 xk 0 0 0. So that's it. So well, so in other words, what this theorem saying is that if a map has constant rank, then it assumes the simplest possible form, which is just projection onto k coordinates. But there is one small thing that I have to remark here, which is that now the maximum possible rank of this, if when you have a map from Rn to Rm, the maximal possible rank is of course M, the target dimension. It can very well happen that this k equals M. If k equals M, then there won't be any zeros here. So here k as k is always less than or equal to M. If k equals M, the zeros that I have put here will not occur. So I'll just get x1 up to xm. Right. So there are two special cases of this. Important. We'll revisit these notions when I talk about smooth manifolds, but for now let me just mention the following, which is that the first case is that rank, that k equals n, the dimension of the domain. Of course, in this case linear algebra tells us that so the image of this, in this case, when I look at the derivative at any point and look at dfp, the image of the entire vector space Rn, the image of that inside Rm, so dfp Rn, this vector space, which has to be a subspace of Rm, has dimension n by definition of rank. Of course, this rank is by definition the dimension of the image. So the image has dimension n, but this is sitting inside Rm. So necessarily m greater than or equal to n. If this happens, we say that if the rank is equal to n for all this thing, then f is called an immersion in this case. So in this case, of course, I mean that k equals n. The second extreme case is k equals m. So in other words, dfp Rn, again dfp Rm is a subspace of Rm, but we are told the assumption is that this subspace has dimension m again. So if you have an m dimensional subspace of Rm, it has to be Rm itself. So this is an onto map. This is onto, and f is said to be a submersion. Here, of course, regarding dimensions, if dfp Rm is equal to Rm, then we know that the rank nullity theorem will imply that this implies actually that n greater than or equal to m. Oh, I should also mention that in the previous case, the immersion case, in the condition that k equals n is an equivalent condition is that dfp, kernel of this dfp is that kernel of dfp is the trivial subspace for all p in U. This again follows from the rank nullity theorem. If the kernel is trivial, then the image of DFP has the same dimension as the domain, and conversely, if the image has same dimension, then the kernel is trivial. Both of this statement as well as the surjectivity of in the second statement follow from the rank nullity theorem. So here also equivalent condition, to say that k equals m is the same thing as saying DFP is surjective, which I have written here. All right, so these are two important cases. I'll give some examples when we talk about these in the context of manifolds. For now, let's just keep these definitions in mind and notice that the constant rank theorem implies that any immersion I'll put it in quotation marks, looks like an inclusion, i.e. x1 all the way up to xn. Remember that in the case of immersion, the target has more dimension than the in the domain. So x1, x2, xn getting mapped to x1 up to xn, remaining coordinates 0. So this map is the inclusion map of Rn inside Rm, and it is the simplest possible immersion. What the constant rank theorem tells us is that given any immersion, it looks like this. Of course, here looks like means that after changing coordinates in the domain as well as the range, like I specified in the last slide, f composed with these two coordinate changes has this form. This is regarding, and this is, yeah, okay. And then similarly, any submersion looks like x1, xn will get mapped to, well, in the case of a submersion, so I just pick out the first m coordinates. This is what is called as a projection of Rn into Rm, i.e. a projection. Of course, these statements are valid only locally. This should be kept in mind. The constant rank theorem does not tell us that, nowhere do we say that on entire U I can change coordinates on the whole of U so that I get some nice form like this. That is not the case. But so this form that I have here is valid only when we pick a specific point P0 inside U. Then I can find this coordinate, another open set V here, and this I get this nice form which I have put here. So that's what I mean by the statement that this is valid only locally. Valid only locally. So that concludes my discussion of the inverse function theorem and its corollaries. For our purposes, that's all that we'll need right now. So the last topic in my set of preliminary topics is C infinity functions with compact support. So what does the support of a function mean? So as usual, let U be an open set. Let's take a function f from U to R, real valued function. the support of f denoted by sub f is the closure in U of the set of all x in U such that f of x is not equal to 0. So as a trivial example, let's look at f from R to R defined by, let's look at the step function. So f of x equals 1 when x is less than 0 is equal to 0 when x is greater than or equal to 0. So in this case, the support of f, the graph of f looks like this. Now the set of all x such that f of x is not equal to 0 is precisely the open interval minus infinity to 0. When I take the closure, I'll just get one additional point, so which is 0. So support is minus infinity to 0. Now I need one more definition. F from U to R is, I'll say it is C infinity if it has partial derivatives of all orders. So of course one knows of lots of C infinity functions. Examples: polynomials in multivariables, etc. So one can take, of course, trigonometric functions, polynomials, and so on. And then you can compose them, do the usual operations. So there are lots of such things, but now what we ask for is something which is not so clear at the outset. We want to know, if there is a given an open set, can I find a C infinity function defined on U whose support is compact? In other words, outside a compact set it's identically 0. Well, surprisingly, it turns out that there are such things. So let me state it as a proposition. There exists a C infinity function f from Rn to R with compact support. So support is, the support of this function is going to be a ball, a closed Euclidean ball inside Rn. So how does one go about constructing such a thing? Of course, I must remark that there is a trivial case which one must exclude here. Namely, if I take the function which is identically 0, then its support would be the empty set, and that would be compact. Obviously, we don't want that. So, in fact, this infinity function that we are going to construct will be identically 1 inside one Euclidean ball and identically 0 outside a larger Euclidean ball. So, the way one does this is, so so let's stop here. So, in the next lecture, I am going to show explicitly how to construct this starting from a one variable function, and then in other words, I will assume that n equals 1 and do this construction, and then it will be easy to do it for any n. Okay, goodbye.